In this section, we're going to be talking about using orbital diagrams to understand the magnetic properties of the various elements, and then we'll discuss any kind of periodic trends associated with systematic changes of the elements. Turns out that if the total number of electrons spinning with a positive 1/2 spin equals the total number of electrons with a negative 1/2 spin, the atom would have 0 net spin, and these are substances that overall have no overall magnetism and are referred to as diamagnetic substances. So here you have the electron configuration and orbital diagram for neon and helium, and both of which have the same number of arrows that are pointed up as the arrows that are pointed down in the orbital diagrams. This is a classic example of diamagnetic substances. If we look at something like elemental oxygen, you have the electron configuration and orbital diagram shown here. The following Hund's rules, you would end up having 2 more plus 1/2 spinning electrons than the number of negatively spinning 1/2 electrons, and therefore this has a net spin and has magnetism associated with it. The oxygen atoms are indeed actually attracted to a magnetic field. If the total amount of spin is relatively small, we would often refer to this as a paramagnetic substance. In some cases, the net spin might be relatively large, and if all of these spins are spinning in the same direction, we can end up having something that might be have ferromagnetic properties, such as iron, which can be used as a permanent magnet. This slide describes the general properties of the metals, which we will contrast to the nonmetals and the metalloids. Metals tend to have a luster, they tend to be shiny, they can be used to make mirrors. They also tend to be malleable. In other words, if you strike a metal with a hammer, they will change shape, but not necessarily break. The metals also tend to be ductile. Ductile simply means can be extruded into a wire, and also probably one of the most important properties of metals is they tend to be excellent conductors of electricity and heat, and oftentimes metals can react with elemental oxygen to form metal oxides, which are the so-called minerals that are often found in Earth's crust. It turns out that metals also generally form positively charged ions by losing their valence electrons. So, for example, elements in group 1A, the so-called alkali metals, tend to form +1 ions, whereas the elements in group 2A have 2 valence electrons that tend to form 2+ ions. The transition metals often will form a variety of positively charged ions, but often have 2+ ions as a very common possible positively charged ion. In contrast, the nonmetals have properties that are nearly the opposite of the metals, and in fact the nonmetals are generally found in the upper right-hand corner of the periodic table. The nonmetals tend not to have a luster, they tend to be dull, they don't readily reflect light. Oftentimes they are brittle. If you happen to have a crystalline solid of a nonmetal and hit it with a hammer, it would crack and break. They tend to be poor conductors of heat and electricity with certain exceptions. So for a really great exception to that is graphite, which can be contrasted with a diamond. Graphite is actually a really wonderful conductor of electricity, whereas diamond is the other form of carbon, and it does not conduct electricity very well at all. In general, the nonmetals, if they can be oxidized, they tend to form acids if those oxides are placed in water. So, for example, if carbon dioxide is dissolved in water, it forms carbonic acid, which gives soda pop its tang. And they tend to be, instead of being solids, the nonmetals oftentimes are liquids and gases or low melting solids. Turns out the nonmetals, instead of losing electrons like the metals, they tend to gain electrons. And so oftentimes they form negatively charged ions. And it turns out that if we first consider the group 7A metals, the so-called halogens, those all have electron configurations where all they needed was one more electron and they would have the same electron configuration as a noble gas. Therefore, the negative 1 ions of those elements tend to be very, very stable. If we go to the 6A elements, oxygen, sulfur, selenium, so on and so forth, those tend to gain 2 electrons to have the same electron configurations as the noble gases. And so those tend to be very, very stable. Likewise, the group 5A nonmetals, they are things like nitrogen and phosphorus and arsenic. They tend to gain 3 electrons to form 3 minus ions, forming these closed shells, which are very, very stable. The third and final category of elements are known as the metalloids. I like to refer to these as the confused elements. They tend to have properties that are somewhere in between the properties of metals and nonmetals. They tend to have somewhat metallic appearance. They have a luster, but they don't conduct electricity quite as well as metals, but they are certainly better conductors than the nonmetals, and so we sometimes refer to these as semiconducting materials. They tend to be somewhat brittle, can crystalline form, they can break pretty easily if you hit it with a hammer, and a great example of this is the element silicon, which we have shown here, and it looks almost like a shiny black metal. Shown here is a periodic table where we would like to compare some of the properties of the elements, and in particular some of the names for the various columns or groups on the periodic table. The very first column, the one way off on the left, is known as the alkali metals. These tend to form the 1+ ions. The group 2 elements are the alkaline earths. These tend to form 2+ ions. These are the only positive charged ions that are commonly encountered. Over on the right-hand side, these are the group 7A elements, the so-called halogens. They tend to form -1 ions. The so-called noble gases, the very, very stable elements that are way over on the right-hand side of the periodic table.